So our next talker is Braden Warwick from Queen's University. He's going to be talking about the effect of stiffener configuration on bulkhead modal parameters.
Thanks, Ryan. So with that being said, I'd like to jump right into things. So the agenda for today's talk, I'll be giving a bit of motivation into my research, discussing what an aircraft bulkhead is, why it's significant, and why we should understand the modal parameters of it. I'll discuss my methodology that I used to investigate this issue, present my results, and then wrap things up with a quick conclusion. So, what is an aircraft bulkhead, and when do we typically see it? So, the main purpose of an aircraft bulkhead is to separate the pressurized passenger cabin from the unpressurized aft section of the fuselage. So as you can see right here in just a generic Boeing aircraft, this pressurized bulkhead contains a significant amount of stiffeners as the pressure gradient between the cabin and the aft section is quite significant at cruise altitude. In addition to that, when we have a rear fuselage twin engine mounted configuration as seen in the Bombardier Global 7000, for example, the engines are directly mounted onto the aft section of the fuselage itself, which introduces a vibration problem where these engine-induced vibrations can then propagate up the fuselage through the pressurized bulkhead here and into the passenger cabin, generating significant interior cabin noise. So of the work that's been done on this fuselage engine-mounted configuration, it's been shown back in 1982 that fuselage-mounted engines contain a significantly higher interior sound pressure level than traditional wing-mounted engine counterparts. In addition to that, the noise has been shown to be tonal, which has been shown to be of greater annoyance to passengers than a broadband frequency noise at the same sound pressure level. So this aircraft configuration is not only louder, but it's also annoying. So let's take a little bit of a look into how bulkheads have been optimized in previous literature. So this started in about 1996 when they first started to investigate optimal plate stiffness and stiffener locations just for generic plate structures. And then this technique was updated in about 1998 with the introduction of topology optimization to determine optimal stiffener location. For those of you unfamiliar with topology optimization, it's basically an iterative technique used to remove unneeded structural elements in order to come up with the most optimal solution that is you can use a variety of objective functions, but typically the most stiffness for the lowest amount of mass. So then this work was expanded upon in 2006 when the researchers then performed shaped optimization on the stiffeners after topology optimization was used to determine the most optimal location. However, the limitation of all this work up till then was that the final design was always compared with an unstiffened bulkhead, which from a practical standpoint is very infeasible in application, as like I showed you initially, the bulkhead always needs to be stiffened due to structural constraints. So in 2016, Duker et al. Were the first to perform a case study investigating a topology optimized bulkhead configuration against a pre-stiffened bulkhead, and they were not actually able to show an increase in performance using this methodology. So another limitation of investigating the bulkhead in isolation is the fact that we're not really too sure how well this actually performs when it's implemented in the aircraft. So a recent journal publication of mine that's currently under review was the first to investigate how well the modal parameters of the bulkhead analyzed in isolation compare to the bulkhead when it's analyzed in a fuselage. So we were able to show that qualitatively the mode shapes agree quite well with a bulkhead analyzed in isolation and then when it's analyzed in a fuselage. And we can see that the MAC and pseudo-orthogonality checks were quite good results as well, and the natural frequencies agreed within about 6.5% on average. So the methodology for this conference publication is to take a bit of a step back from the topology optimization approach and to understand bulkhead modal parameters at a more fundamental level, and to see how these modifications in stiffness affect the overall modal parameters. This is the original bulkhead that was analyzed in my journal publication. So as you can see, there's 7 vertical stiffeners and 2 horizontal stiffeners. This was just based on a generic aircraft structure. So for the purposes of this investigation, we took 2 modifications of this, one with no horizontal stiffeners and one with just 1 horizontal stiffener. So the modal analysis procedure, I first collected experimental data used to validate a computational model. So the following procedure was followed. It's just the standard model correlation techniques of first determining the correlated mode pairs, which is just qualitatively which mode shapes physically match up and look similar. Then I performed a natural frequency comparison of the correlated mode pairs using a linear regression. Then I examined the mode shapes on a quantitative level, first by using the MAC, which determines the overall noise in the system of eigenvectors. And then I performed a pseudo-orthogonality check, proving the orthogonality relationship of the computational eigenvectors and the experimental eigenvectors with respect to the mass matrix. I used the system equivalent reduction expansion process to reduce the size of the computational eigenvectors down to the system of experimental eigenvectors. So the experimental setup I used, I want to ensure consistency between all 3 bulkhead configurations, and I did so by applying the same boundary conditions. So we simulated experimentally free boundary conditions by the use of these soft elastic bands attached with carabiners here. We used 36 evenly distributed degrees of freedom on the bulkhead on all 3 configurations. We analyzed a frequency bandwidth of 0 to 75 hertz just to give us enough modes to be able to validate the computational model. And then there's a little bit more detail about the experimental equipment that I don't really want to get into. So I used the same computational methodology that I proposed in my journal publication. So I first used free boundary conditions to validate the computational model with the experimental data. And then I moved on to imitate the boundary conditions found in operation, and then performed the modal analysis again. And I investigated the frequency range of concern, which is the engine excitation frequency. For the computational setup, once again, I ensured consistency between all 3 configurations. I used shell elements. Same eigensolver was the Lenqua method. The mesh properties, as you can see, primarily quadrilateral elements, and roughly the same amount of elements. I used bound contacts to connect the stiffeners with the plate of the bulkhead, so I neglected all the riveting coupling effects. So the results of this study, so first the model validation. I found 9 and 5 correlated mode pairs for modifications 1 and 2 respectively. A linear regression of the natural frequency data produced lines of best fit with slopes of 0.91 and 0.83 for modifications 1 and 2. And I found 6 and 5 modes produced pseudo-orthogonality terms greater than 0.8. This is for modification 1 and modification 2. So based on these results, for the intents of this study, I considered the model to be validated. And I'll identify the cause of discrepancies here between the 2 data sets. So first I want to highlight that the first modification generated better natural frequency results, whereas the second modification generated better orthogonality results. Some of the key computational assumptions that I made, which likely contributed to the majority of those discrepancies, were that the eye bolts were not modeled computationally. So you can see here there's actually eye bolts bolted into the bulkhead, which are used to connect the carabiners, which are used to imitate the free boundary conditions. And that was another huge limitation of this study, was that obviously there's going to be some constraints here at this location of the bulkhead, which was not considered computationally. And then once again, the rivets were not considered computationally. but as like you can actually, if you look close enough, you can see there's small gaps here in between the stiffener and the plate, which is cause for coupling to occur between the stiffener and the plate of the bulkhead, which can shift some of these natural frequencies around and cause significant discrepancies between both the mode shapes and the natural frequency results. So to assess the origin of these off-diagonal and pseudo-orthogonality terms, I performed individual orthogonality checks between the two data sets individually. So the computational orthogonality check produced the identity matrix as expected, whereas the experimental orthogonality check produced pretty significant off-diagonal terms due to the issues that I addressed on the previous slide. So when we combine these two together, we see that these off-diagonal terms stay on the same order of magnitude as they were here. So once again, likely due to the issues that I addressed. But for the purposes of this work, I don't really consider it super important to investigate rivet connections and so on and so forth, because that's a whole nother wormhole that I don't want to get down. I want to investigate these stiffener effects on the bulkhead. So then when I went ahead and applied the operational boundary conditions to the computational model, I want to identify some of the key results. So as the mode number increases, the complexity of the mode shape obviously increases as well. And if you remember the modifications, this one had no horizontal stiffeners, this one had one, and this one had two. So there's a stiffness increase as we go left to right here. So the key results that we found were that the first two modes actually decreased in natural frequency, which meaning, if we remember our definition of natural frequency, that the mass term had the added mass had a greater effect than the added stiffness. I believe this is due to the displacement of these mode shapes in particular, because we see very global modes. We see where the mass inertial effect would be a lot more significant in this case. Whereas when the modes get more complex, we see that the natural frequency actually increases as a function of stiffness. Therefore, the added stiffness effect becomes has more of an impact than the added mass. Now, this can also, this is likely due to, once again, the overall decrease in global displacement. As the mode gets more complex, you're introducing more nodes locally throughout that mode shape. And then I wanted to address one more point, that the frequency increase is not consistent. So as you can see, there's a pretty small increase here, whereas some of these increases are on the order of 30 to 40%. So it's important to keep in mind that the frequency increase will be inconsistent from mode to mode, and it has a large relationship with where you add the stiffener and correspondence to the modally active regions of that particular mode shape. So when I went ahead and investigated the engine excitation frequency, I assumed it to be, I analyzed within 10% of 117.7 hertz, which I took to be the engine excitation. So the first modification actually increased the modal density within that range, so that's not what we wanted, so I didn't consider that design any further. But the second modification maintained consistent modal density with the original configuration, in addition to reducing the overall mass of the stiffeners by 12.2%. So for the intents of this investigation, I consider this to be the optimal design. However, I have not performed any structural considerations, so that would obviously need to be taken into account. So in conclusion, the key points that I want to take away from this investigation are that optimizing stiffener location is a non-intuitive process that's highly dependent on the location of the modally active regions of the bulkhead. So it's important to understand all of these effects when performing an advanced analysis technique like topology optimization. So if the goal of topology optimization is just to shift all of the natural frequencies above a certain threshold, it becomes less of an effect. But if we're trying to, like in this case, where the engine excitation frequency is in between several modes, we really need to understand what mode shapes are in that range of concern, because different stiffener configurations will affect those modes in different ways. So we really need to have a fundamental understanding of how that those interactions come into play before we start performing more advanced techniques. The future work that needs to be performed here is definitely the structural considerations, which I didn't take into account. Here's some of my references. I'd like to point out my journal publication currently in review, so if any of you guys are interested in this work, please check that out once it gets published, which should be quite shortly. I'd like to thank Bombardier Aerospace, NSERC, my co-authors, Dr. Il-Young Kim and Dr. Chris Machewski. All right, thank you. Are there any questions?
Thank you for that presentation. Any questions for the speaker?
Yep.
Is there a question?
So, what kind of computational effort would it take to start to integrate the modal analysis into a topology optimization?
That's a pretty standard procedure. So it's on the same order of magnitude as a standard topology optimization investigating compliance or with a volume constraint. It's not too much more in depth, especially if you're just investigating shifting the natural frequencies up, like placing a constraint on the natural frequencies. That shouldn't add too much more computational demand. But just this work is more so showing that if you want to place a constraint on a natural frequency, say like shifting them outside of a range from a minimum to a maximum value, you need to understand what these mode shapes look like and where you might be, like what the design space is and where the optimization code might be adding material or taking it away, because it will definitely play a role. But the computational demand shouldn't be much greater.
So it's more on the exploration.
Yeah, it's more so like a preliminary analysis that you need to perform, which isn't that computationally demanding as the standard modal analysis, but you just need to have that understanding prior to going into the topology optimization. Yeah. Are there any other questions?
Okay, let's thank our speaker.
All right.